let's now try an example of how we would actually apply this particular law. And for our first example of Ampere's law, we're going to choose our favorite example. So our example number 1 is going to be, once again, the infinite wire, done now a third different way. The goal, though, here is for you to take a familiar context and then kind of see how convenient, and also we can focus on the details of the procedure we use when applying Ampere's law by working with a familiar example. So once again, our example will be, but this will be the last time we use this one, I promise, right? We're going to have an infinite wire carrying a current I here off to the left. And our job then is going to be to find the magnetic field for this thing at some particular position, say at some distance r away from the center of the line. So we're going to be at a distance r here. And the question is, what is the magnetic field then at that particular position? Now, just as with Gauss's law, we have a recipe. And if you carefully follow this recipe step by step, every time your Ampere's law will get you a result for the magnetic field. So let me kind of gather all of those step-by-steps on one frame over here. So the recipe then is actually extremely close to the recipe that we follow step by step for applying Gauss's law. It's just a little bit different. So the first thing we always do when we do Gauss's law, recall, is we need to know and understand the symmetry of the system and the symmetry of the field. So we begin by using the fluid model to understand the field lines. In other words, to picture the field lines. So in this case, we would look at our wire here, right? We would use our fluid model, which would mean we would take this wire, we would imagine starting to rotate it according to right-hand rule number 2. So I stick my thumb along to the leftward direction, and my fingers curl around in a way that we would be setting this thing. Here I'll kind of draw it even as a little tiny cylinder in my fluid model, right? And this tiny little cylinder is going to be rotating in such a way that the way my fingers would curl, they come up in front and they go down in back, like so. And I indicate the down and back by the fact that I can't see this line as he goes in behind where the circulation would be downwards. I then imagine that he gets spinning and churning up the fluid, and as he churns up the fluid and begins to drag the fluid around with him, very clearly what's going to be happening is it's going to carry the fluid around in circles in that same type of a circulation pattern, like so. So the field lines all have this circular appearance all the way down here as I go down around my line. Okay, so that's the first step. Now, second step in Gauss's law is to pick a Gaussian surface. In this case, the basic integral form of my law, notice, is not an integral of the field over a surface, but around a path. So I have to pick not what's called a Gaussian surface, but I have to choose what's known as a closed Amperian, instead of Gaussian, but Amperian loop. Because it's supposed to represent, remember, the boundary of some area. It's the edge of some area. It's a path, a closed path that I'm integrating around. And when I choose that loop, the same kind of rules apply that applied for Gauss's law. The first rule is that it has to pass through the point of interest. If it doesn't pass through that point, then I can't guarantee that I'm going to be learning anything relevant about the field at the point that I want. So it has to pass through the point of interest. That's the first thing. The second thing is that just like Gauss's law, you'll notice that we have a dot product involved. That dot product we would like to work out simply in our favor, with a cosine always giving us 1 or 0. That means we have to pick a path. The path has to be always either perpendicular or parallel to the field lines. So, and number 3, we want this to, of course, enclose some current. Otherwise, we will just get 0 equals 0. So it should enclose some current. Previously it was charge, but now, of course, it's current that we're focused on. So let's see here. So here's my point of interest. I want to always move parallel or perpendicular to the field lines. In this case, the field lines are these circles. So that's easy. I can just pick a circle that goes through my point of interest. And the nice thing here is that if I follow that circle parallel to that field line all the way as it goes behind the wire, back out in front, it will actually close back on my point. So in this case, I don't have to take any right angles to peel off from the field direction. I can just be always parallel to the field direction. So that makes a nice Amperian loop. And finally, you'll notice that it very naturally encloses, or if you want to think of it this way, like a lasso, right? Like a cowboy's lasso. It lassos or encloses some of my current. It goes right around the wire. The wire pierces through the area of my loop. Good. So I've picked my Amperian loop. The last step, of course, is then we're going to write down and evaluate Ampere's law. We write it down, we simplify, and solve for the magnetic field. So far, of course, we've managed to picture the field lines. We've chosen our loop, and as we said, it went through the point of interest. It was always parallel, in this case, to the field lines, and it definitely enclosed some current. So now we're focused on step number 3. So let's write down Ampere's law. So I'm going to have the integral around my loop of B dot dl. And this is going to equal then the enclosed current. But actually, you know, just like Gauss's law, it's helpful to write this in a particular order. It's most helpful, actually, to write first the current term, mu naught times the enclosed current. Now there is this additional term, and for now, until we come back to it, we can ignore it, right? There's that displacement current term that we've said is generally quite small. It has a factor of 1 over c squared in front of it. And this then is going to equal the closed line integral of B dot dl. You can write it in any order. This just seems to help the organization a little bit better. All right, now, in our case, if we think about the enclosed current through our loop, what we see is that we consider, remember, the area that my loop encloses, and the goal is to look through all currents that pierce through that area. And as you can see, it is precisely this one wire going through the area. So I have my current then. So that's just mu naught times I. But just like with circuits, whenever you're dealing with currents, you want to be very careful about your sign conventions. So I put a plus or minus to indicate I've been checking that. And when I look at my path, notice that if this is my area, by right-hand rule number 2, my normal vector then would be pointing this way, n hat. So I'm actually going to allow myself to circulate around this loop in precisely the direction of the magnetic field. In that case, my normal vector to my area is off to the left. By curling my fingers around that loop, my thumb would then point leftward. And this is the key. The sign of the current, the sign that we have to assign to the current, is positive if the current goes through in the positive normal direction, which is what's happening in this case, or it's negative if the current is actually flowing in the opposite direction from it. But remember, the current is actually flowing here in the same direction as n hat, so I can safely choose the positive sign in this particular case. I'm going then, of course, to ignore the small term until we come to a point in the course where that term can become significant. And then I'm left with the integral of B dot dl. And that integral, of course, as you guys know, we carry that out in the same spirit that we've done in Gauss's law. We break out the dot product, magnitude of b times the magnitude of dl times the cosine of the angle between them. In this particular case, the way I've chosen things is my path goes around in this direction, and that path I chose, when I chose this direction for n hat, right, that path I chose is following the field line. So the path, each little chunk of my path here, is always automatically aligned with the magnetic field. So the angle between those then is 0. And the cosine of 0, of course, then is 1. The magnitude of b, fortunately for us, is going to be constant. That's because of the symmetry here. We made a loop following that field line. It very nicely kept itself as a circle centered on my wire, so the distance from the center is always the same, and therefore by symmetry the strength of the field should always be the same. So that's going to be a constant, which we then can pull out, and it's also equal to this b of r that we're trying to solve for. And finally, the magnitude of dl, that's just my path length going around the loop. So what we're left with is that mu naught times the current I is equal to the magnitude of the magnetic field at this distance r, which we are trying to compute, times the integral around my closed path of the little lengths that make up my path, dl. Well, that total sum of the magnitudes of my dl's, of course, is going to be nothing other than the total distance that I travel around my loop as I break it into a whole series of tiny chunks. So that would be the circumference of that circle. So this will be just 2 pi times r. And now that I've written everything down and evaluated, of course, the final step is to solve for the magnetic field, which we now can do very easily. The magnitude b of r is exactly what we've been seeing all along. Our famous result we've derived several times now. It's mu naught I divided by 2 pi r. 2 pi times the distance to the center. Exactly what we would expect. So now we can draw our happy professor symbol, because this is much easier than doing that nasty integral that we have to do the bios of our